Hello everybody, my name is Ricardo Rocha. I'm presenting WebLab number 2. Well, in this experiment I considered the fall of a wrapped t-shirt which had a mass of approximately 180 grams. As we can see here on tracker, we have the position versus time graph. This is with the y-axis. Here we have the time and the vertical positions. From tracker, I can obtain the total time, which is 0.634 seconds, and the total height from where it was released, which is 1.88 meters. With this information, I went to the first model, where I didn't consider drag. Here I define the mass of the object, the initial position, the initial velocity, acceleration due to gravity, 9.8 meters per square seconds, and the j-hat vector, which is a unit vector on the y-axis that has a magnitude of 1 on the y-axis. As we can see here, the drag constant is going to be 0. So for the loop, I define the weight, which is the object's mass times acceleration due to gravity times the j-hat vector. Then we had drag force, which is the drag constant times the object's velocity. In this case, it's a directly proportional relationship. So the net force in this case, since this constant is 0, will only depend on the weight. When I run this program, I will get something that looks pretty much the same as the thing obtained on tracker. Here we can see the object falling down, and here we can see the position versus time graph. It looks pretty much the same as the one obtained on tracker. Then for the second model, I had to consider drag. Here I got a drag constant of 0.041, which is the value that gave me the final position that was obtained on tracker. When I run this model, I will get the same situation, but I will show you right now the final position. Here I can see the weight pointing downwards. So as the object falls down, the drag increases. Is pointing upwards. Then this is the final position that I told you before. It matches with the final position obtained here on tracker. So this value of 0.041 for the drag constant is a very good value. For the third model, we were asked to consider that drag force depends on the square of the velocity. I had some trouble to perform this model, but in the end I think that I could finally make it. The thing that I had to do was to define the magnitude of the velocity using this command ABS. Then with this magnitude of the velocity, I just multiply it twice in order to make the square of the velocity times the new drag constant, and that gave me the magnitude of the drag force. So with that magnitude of the drag force, I just multiplied times the j-hat vector. So now the net force depends on the weight and on the new drag force. So when I run this model, it runs pretty well, but the only thing that I couldn't make, I don't know why it didn't work, was the arrow of the drag force pointing upwards. I don't know why it didn't appear. So with all this information, I extract all this data into a spreadsheet. I use an Excel document. So the first graph that I made was the tracker data, which is the red dot line, then the model data, which is the blue line, and this case is no drag, and the model data with drag, which is the green line. We can see here that the tracker data is below the two graphs at the beginning. Then in the end, it seems to match with the model data that considers drag. I compared the two graphs in the case with the first drag, the case with the second drag. The green line is when I consider that drag depends only on the velocity, and this one depends on the square of the velocity. Here we can see that this graph is higher than this one. This is because the constant was bigger than the one obtained here, which in the second case of drag was a very small value, was 0.00, a lot of zeros, and 2. So this is why this graph is higher than this one. Then in the end, I put everything together. I put the track data here, is a red dot line. Then the green line is the model data in the first case of drag, and the purple line is the model data in the second case of drag. As we can see here, drag is a very important force to be considered. because it pretty much slows down the fall of an object. And this is why the skydivers, when they jump, they don't accelerate forever. They have something called terminal velocity, which is when the drag force matches the weight of the object, and in the end they fall with a constant velocity. In this case, we couldn't see a terminal velocity because the height was very small. Well, I hope you like this video. Thank you very much.